All right, everybody, welcome. So today we're going to talk about how to solve integrated rate law problems. So again, we are trying to find the rate law, the rate constant, and the order of a reaction. And the data that we're provided with is time versus concentration. Okay, so in this particular problem, it says the decomposition of hydrogen peroxide was studied, and this data was obtained at a certain temperature. So I have the data for time and the data for the concentration of the reactant. It says to determine the rate law, the integrated rate law, and the value of the rate constant. Then calculate the concentration of hydrogen peroxide at 4,000 seconds after the start of the reaction. So there's kind of a lot going on here. The first thing is that if we are given time versus concentration data, we're going to need to use our graphing calculators. So I'm clearing mine out right now. All of your lists need to be clear when you start. Okay, so again, to get started with this, what you're going to do is go to Stat and then go ahead and click Edit. And for list 1, you're going to put the time. So first one here is 0, and then 120. Now I know that says plus or minus a second, but that's just giving you a margin of error. You don't actually put that part in the calculator. Just be aware that it might not have actually been taken at 120 seconds. It might have been at 119 or 121. So 120, 300, 600, 1200, 1800, 2400, 3000, and 3600. Okay, so those are the times. For list 2, so I'm just going to use the arrow to scroll over. For list 2, I'm going to input those values for concentration. So we start off with 1, 0.91, 0.78, 0.59, 0.37, 0.22, 0.13, 0.082, 0.05. And I realize that this one had an additional significant figure, but your calculator is going to go ahead and take that out anyway. So if you have significant zeros at the end of your number, unless they're there as a placeholder, your calculator is going to take them out. So I just never put them in. All right. So that's going to be our first list. But I'm going to go ahead, and the way that rate law works is if I graph list 1, the time for X, and I graph list 2, the concentration for Y, and I get a straight line, then my reaction is going to be 0 order with respect to the hydrogen peroxide, the reactant, okay? But I'm going to go ahead and in list 3, so I'm going to scroll over to list 3, and I'm going to highlight list 3, and I'm going to program the natural log of list 2. So I'm going to do the natural log of our data in list 3. And then in list 4, I'm going to do the reciprocal. So I'm going to do 1 divided by all the values in list 2. And so that's going to go ahead and take the reciprocal of all of our concentrations and program that for list 4. Okay, so list 2 is concentration. List 3 is the natural log of those concentrations, and list 4 is the reciprocal of those concentrations. So then I'm going to go to Stat and scroll over to Calc, and I'm going to do a linear regression. So I'm going to hit 4. Now first I'm going to check list 1 versus list 2. So let me change that. Again, if this is linear, then that means that it's 0 order. But if I check the R squared value, that's really not that close to 1. So the R squared value closest to 1 is going to be the most linear line. And so for this one, I don't think that's it. So I'm going to do Stat, Calc. Again, I'm going to do a linear regression, but I'm going to change my Y value from list 2, which was concentration, to list 3, which was the natural log of concentration. So then if I look at that one has an R squared value of 0.9997, which is really close to 1. So I'm going to say this is probably going to be first order. If time versus the natural log of concentration is linear, then it's a first order reaction. But just to be sure, I'm going to go ahead and go to Stat, Calc, Linear Regression, and I'm going to plot, I'm going to go ahead and do a linear regression of list 1 and list 4, just to check. Okay, so before we had an r squared value of 0.9997, this one's 0.87. I think this is actually the worst r squared value. So I'm going to say that when we did list 1 and list 3, which was the natural log of our concentration, we had the highest r squared value, so that's going to be our most linear line. So what that means is that this is first order with respect to hydrogen peroxide. Okay, again, if it's time versus concentration that's linear, 0 order. If it's time versus the natural log of concentration that's linear, then it's first order. And if it's time versus the reciprocal of your concentration, then it's second order. Okay, so this is first order. So what I'm going to go ahead and do is the integrated part of the rate law. So since I already have my slope and my y-intercept here, I'm going to go ahead and do the integrated rate law. So my integrated rate law is going to look like the equation for a line. Since it was the natural log that was linear, that's what I plotted. It's the natural log of hydrogen peroxide concentration is equal to, and then my slope, which is negative 8.35 times 10 to the negative 4th. Don't forget your exponents, check for those. T, because we plotted time for x. And then if I look at my b value, it's negative 0.00493. So I'm going to do minus 0.00493. So that would be my integrated rate law. Again, that looks like the equation for a line. Okay, y equals mx plus b. For the rate law, just the regular rate law, aka the differential rate law, it always looks like rate is equal to k times the concentration held to some exponent, and that exponent is the order. Well, for us, we know that rate is equal to the concentration, or I'm sorry, k, right? Which is the slope of this line. So that's going to be 8.35 times 10 to the negative 4th times the concentration of H2O2 held to the first power. Now you don't have to put the 1, but you can. This is first order, and so the exponent is 1. Okay, and remember that the slope is always the rate constant in these. So you can go ahead and plug that into your differential rate law. It's always a positive in the differential rate law, so just be aware. Okay, so we did rate law, we did integrated rate law, but now we need the value of the rate constant. So K would be 8.35 times 10 to the negative 4th. Now, if I look at this, I had time and I had moles over liters as my units here. And so I know my rate is always going to be my concentration divided by time, which in this case was seconds, that's the unit that we were given for time, is equal to K times, and then we had a molarity here. So to me, it looks like the unit for K only needs to have seconds on the bottom to turn this into moles over liters times seconds. So I'm going to go ahead and say that the unit for K is going to be 1 over seconds, or 8.35 times 10 to the negative 4th seconds to the power of negative 1. So sometimes if you see the unit on the bottom of that proportion, then you can write it out like this with that negative exponent. Okay, so that would be the value for the rate constant. It's just the slope of our line. And then we need to calculate the concentration of hydrogen peroxide at 4,000 seconds after the start of the reaction. Well, using our integrated rate law, since we have a time, and time is a variable in the integrated rate law, we can simply plug in 4,000 seconds for t, and then solve, okay? So, natural log of H2O2 equals negative 8.35 times 10 to the power of negative 4th times 4,000 minus 0.00493. So I just need to plug that in my calculator. So negative 8.35 times 10 to the power of negative 4 times 4,000. Okay, minus 0.00493. Oops, sorry. Do that again. Minus 0.00493. Okay, so I get the natural log of my concentration is negative 3.34. Okay, no exponent on that number. Now that's the natural log of my concentration, but I need to know the concentration. So the thing is, if we hold anything to the power of e, right, so e to the power of our number, that's the opposite of natural log. So if I do e to both sides, that'll cancel out. So if I do e to the power of negative 3.34, that's going to give me the concentration of H2O2. So E, answer, and I get 0.0353 if I round that to 3 sig figs, okay? So that would be our concentration, and again, our concentration was given in units of moles per liter, aka molarity. Now, does that answer make sense? Well, let me think about it. 4,000 seconds would be after the data that we have available. And so what should be happening to the concentration is that it decreases over time. So if my time increases, then my concentration should actually be less than 0.05. And the value that I calculated is less than 0.05. So this seems like a viable answer. You can always check your work that way. Let's say that we were given a time that was in between 2,400 and 3,000. So let's say they give us the time at, I don't know, 2,800 seconds. Well, then my value for concentration should be somewhere between these two values for concentration that were measured. So you can always check your work that way to see if it makes sense. And in this case, since our time would be 4,000 seconds, which would be greater than what we have, then our concentration should be less than the last value we have. So I hope that helps.